Here we are again. Here's our textbook, Logics for Computer Science, Classical and Non-Classical, Springer 2019, and I'm the author. And we are already in chapter 6. So chapter 6 is about the automated proof systems, and will prove completeness of classical propositional logic. And here are our plan. We have different parts. So part 1, we'll talk about proof system RS, which is very nice proof system. And we'll talk about automated search for proofs and define what's called decomposition trees. And then part 2, we will talk about and prove, we'll talk about strong soundness and constructive proof of completeness theorem. And then we will do some other similar proof systems just to accustom you to syntactic differences and what do they mean. As the next, we will cover Gentzen's sequent systems, which are classical work, and also show that that can be the strong soundness and constructive proof of completeness, also how you can carry it for these systems. And finally, and it's not finally, in part 5, we will talk about original Gentzen system LK and LI, which he invented, and prove different way the completeness theorem for his systems. And then he proved what is famous Hauptsatz's theorem, which is called main theorem, which allows to change those systems into the systems for which the automated theorem proving is possible. And so here we are, part 1. We do the proof system RS. So introduction. Hilbert systems are easy to define, as we did in previous chapter, and admit different proofs of completeness theorem, but they are difficult to use by humans, and I think that you notice that, not mention the computer. And of course, the emphasis is on logical axioms, keeping rules of inference to minimum. In our system was only modus ponens. There are a little bit more rules for predicate logic, but this is really minimum. Gentzen style proof systems reverse the situation by emphasizing the importance of inference rules, reducing the logical axiom to absolute minimum, usually 1. And so they are less intuitive, but they made possible the automated theorem proving, and that's why we study them. And we'll talk about, there wouldn't be automated theorem proving, or there would be, because somebody else probably would invent similar thinking about proof systems later. So Gentzen formalizations, as they are also called, were invented by Gerhard Gentzen in 1934. That's why we call them Gentzen style, because the idea was invented by Gentzen. And so in original Gentzen work for classical and intuitionistic predicate logic, was for classical and intuitionistic predicate logic, and he introduced a special expressions called sequence. When I type sequence, always I get call for spelling mistakes. That's why Gentzen style system using sequence as basic expressions are often called Gentzen sequent formalization. And we will do it in the slide set 2, we will do our own version of original Gentzen, which is much more modern and more understandable, and will prove their completeness. And also we then will do, as I said, as the next step, we will show also original systems, so you will see that it's the complexity of it. And also I will show, but I don't think we'll have time to go in details about it, but it's important for you to know that it exists, the Gentzen-Hauptsatz theorem, which is called cut elimination theorem. I included it, and I will give it to you because there is, I found only one modern book which had it too. So, and they are very mathematical books, so I think it's very important to know that technique, which is very powerful and still being used when people invent new logics and try to prove completeness theorem for their Gentzen type formalization for new logics. And that would be the whole slide, whole piece. So, propositional version of historical Gentzen original formalization for intuitionistic logic is presented in chapter 7. So I will talk about it next time. And original classical and intuitionistic predicate logic systems are discussed in chapter 9. That is when we get into the predicate version of classical and non-classical logics. So other historically important automated proof systems which I present here, which are RS and QRS, I call it like that, because they are due to Russia and Sikorski, R for Russia, S for Sikorski, and it's a famous work published in 1960. So they were first to give a constructive proof for predicate logic, not only for propositional logic and predicate logic through those systems, and of course the automated theorem proving systems, they are very, very powerful and very nice, but also they are easier to understand as the first approach to that type of proving system than original Gentzen sequence. So that's why we start with this type of formalization. And so what I say, that the historical importance and lasting influence of Russia and Sikorski works lays in the fact that they were the first to use proof searching capacity of the proof system to define a constructive method of proving completeness theorem for both propositional and predicate classical logic, and that's what we are going to do today. And you'll see in, I don't know, half an hour, you will have it. So this is much easier than Hilbert type proof system, especially the proof 2, which I show you how difficult it is. And also we generalize that constructive method to Gentzen type sequent calculus, and we'll discuss it later. And completeness for classical predicate logic is in chapter 9, and we'll get to there later. So here's the proof system. Language, we have our full language, negation, implication, conjunction, disjunction, and expressions now are E equal F star. What is F star? F star is the set of all finite sequences of formulas. So we have a notation. We write here is F star, and notation we elements. So now our elements of the proof system are finite sequences of formulas, and of course we have notation. We use gamma, delta, sigma. Now they denote finite sequences of formulas. So that is important to remember. And of course, you have semantic links because we want to prove semantics. So we have to extend our semantics to the expressions, and the sequence is gamma is a sequence of formulas, and we write delta gamma disjunction of all formulas in the sequence. So it's not really formal, but you think about comma in the sequence as disjunction of all formulas. And so formally, just to have some formality, it means the formal semantics. If you have truth assignment, which is on variable, V star is classical semantic extension to the set of formulas, and now we have to extend V star to the set of all finite sequences, and we put V star of gamma is V star of disjunction of all formulas of gamma. So it is a nice formal simple definition. And then normally we define the model. We say that V is a model. V is a model of the sequence gamma if V star gamma is T, and the same contramodel, V star gamma is F. That we can put this because we are in classical semantics. And of course, we have to define semantics, as we remember. The definition of semantics leads to the definition of tautology. So that's a sequence we say is tautology, and we denote like that if for all V star gamma equal T. So for example, that's very difficult example. If we have, this is our gamma, it's a sequence of formulas, and we have truth assignment on A, F, and on B, T, and then you compute normally V star gamma, in shorted notation is you get this, and you have that is F. So, and so we exercise, given a gamma, and a truth assignment, prove that V satisfy gamma, so that you just evaluate the same way as we did in a minute ago. Of course, you see that I'm just showing you that when you in my lectures and in the book, there is a lot of exercises like that, and then which are immediately followed by the solutions. It means this is like full-fledged solution. This is definition of V, this is extension, this is nicely written. So finally we get T. So we proved that this sequence gamma, this V, which we had, satisfies the sequence gamma. And now we have, so that is our semantics, extension of the semantics. And we have two rules of inference, two types of rules of inference. One type is one premise rule. It means you have certain sequence, you deduce another one, and there is a two premises rule, and you deduce. Now, in those systems, there are special, those rules of inference are very special rules. It means each one introduces a new logical connective or negation of the connective. So that's why we denote the names, these are the names of our rules, would be disjunction. It means the rule introduces disjunction into the sequence of formulas. This is negation of disjunction, conjunction, negation of conjunction, implication, etc. So that's why we name those rules like that. And another important vocabulary is the word literals. Any propositional variable or negation of propositional variable is called a literal. We use that language, which came much later. That language belongs to the field of automated theorem proving, of the technique of proof system, which is based on resolution, and it's based of language prologue, so that's why we use the same language, because we don't have time to cover everything, but we use already the language of resolution. So literal, it is variable or negation of propositional variable. Variables are called positive literals, and negation are called negative literals, and that is the language we are going to use. And we have special notation, which we're talking about syntax, so you have to be very, very careful about using, defining and using the proper notation, because I define it once and I'm not going to talk about it any more. Of course, I will repeat it from time to time. But this is like declaration. When you, in your program, you declare your variables, you have to use them as the way they've been declared. So our now prime, you see, this little prime means that these are finite sequences of literals. So mathematically, gamma prime, delta prime can have indices, are LT star, it means finite, this star means finite sequence of literals. And otherwise, if you don't put prime, means they can be any formulas. Of course, literals are formulas, but that must be only literals. And logical axiom, as I said, is really one axiom. So one axiom, it looks like this, that if you have a sequence of literals which contains a variable or negation of variable, it is our axiom. Why? Because our semantics was disjunction. So A or not A is a tautology, so axioms are tautology. And then I wrote it in it's enough to say this, but we wrote it like that, just to stress that you have only literals. You see, you have everywhere prime, and then the order, because the sequence, the order of A and not A is not important. And again, A, I like the letter A, could be P, Q, I1, whatever, is any propositional variable. So really it's a scheme, infinite schema of axiom. And so that would be our, and of course semantic links, and you can evaluate that. Here's evaluation, that this is always true. So the axioms are tautologies, all the axioms are tautologies. And rules of inference. So I'm going to come back to those rules, but I want to tell you what does it mean that that rule introduces a connective. It means that here you have a sequence, and a conclusion can put between A and B a disjunction. So that is a new formula. So that sequence introduces the disjunction and introduces it in a certain way that here, to be able to apply this rule, you need on the left side, you need to have only literals. And negation of disjunction, if you have not A and you have not B, you can deduce not A and B. So if you want to really to remember, and you have to remember those rules, so you can think about them like that, that, for example, disjunction rule has something with primes, literals, you have A, B, and you have sequences, and you can write A, B, but this is the same information. You keep all the information around. And for two premises rule, you have our gamma prime, and you have not A, and you have our delta, which is, and you can see the second premise needs to have the same, and the difference at that part, you see, this part is the same. So you have, like in the sequent, you have information. The information on both sides have to be the same, that it says that you can deduce, you can think not A, and this is two premises and not B. You know that this is logically equivalent to what? Not A or B by De Morgan law, so you can deduce negation of A, B, and you keep your all information around exactly the same. So the genius of Gentzen was to have deduction where you keep your information constant and you only do something about the formulas. So that's why the rule is called negation of disjunction. You have not A and you have not B. You can deduce not A or B. So you introduce not A or B. That's why you have not negation. So that is the thing to remember, that those rules come with the information which always has to be the same, and you carry that information around with you. And this is really not A, not B. You can deduce not A, B, and you have that this is logically equivalent. And then you have the same information around. You have some information here. You must have the same information here, and you carry that information with you all the time. So they look complicated, but they are less complicated than they are, because they are based on very basic logical tautology. That means you have A and you have B, you have A and B. You have not A or not B. By De Morgan law, you have not A and B. And so if you remember, and then you carry your information with you. So those rules look more complicated than they are, but the meaning, like for example, when you have the rule for the implication, if you look the rule for implication, I spent a little bit of time on that, because once you have it in your head that those gamma prime, delta, all these things are just information you repeat, that the rules are really, really obvious. So implication rule would be if you say I have not A, B, and you have some information, and here another information, I can deduce not A or B is logically equivalent in classical logic in the implication. So you replace, and by semantics, this comma is or, so you can deduce in logically equivalent way. A implies B. That's why the name is implication. You can deduce from this implication, and you carry all your information around, and that is now those gamma prime. So this is your information. Carry the information around, but here important, gamma prime are literals. So they're only variables and negation of variables, and here you have any formula. So you can see this is a first formula. These are the first formulas which are not literals, which are not variables. So that is a syntactic structure, and it's nicely written here. you see gamma prime is the sequence of literals, delta is any formula, and A, B are any formulas. So here's our system, and defined. You have language, expression are finite sequences of formulas, logical axiom we already defined, a sequence of literals which contains variable negation, and you have 1, 2, 3, 4, 5, 6, 7 rule of inference. Each introduces connective or negation of connective, except for a double negation, and double negation is only one, because you cannot introduce just negation. You introduce double negation, and which says that if you have A, you can write double negation of A, and you have your information. Here you have your literals, can be empty. Gamma prime is in F star, so empty is here, so it can be empty. And delta is the same in F star, also can be empty, and you carry your information. And you see this is that A is logically equivalent, not A. Very classical equivalence. So you can see already immediately that you cannot have such a rule in intuitionistic logic, because that is not logical equivalence in intuitionistic logic. So it's very beautiful, very powerful, but is extremely close to classical logic. We can use it in modal logics, because the non-modal part of modal logic is based on classical logic, and then you add modal connectives and modal rules, but that's another subject. So, and you have formal proof. I am not. Again, when you read the slides, I repeat certain definitions, like this one. We've done it already 5 times in previous chapter. I just repeat, just to have that you can have all information needed at the given moment. So that's why sometimes you have some repetition. And you write as usual, gamma has a proof for the formal proof, and so on. And we write here in the definition of formal proof, there is formal proof really would be the sequence of sequences, right? Comma, comma. Because here you have already commas, because this is a sequence, so we write a formal proof with a double like this, because to know where that premise, that sequence ends and a new sequence starts. So that's why we have. So, and now we introduce a new notion of a proof, which are called a tree proof. So instead of writing sequences, we will be writing trees. And I will show you, for example, our proof would look like that. It means that you have axiom, and you apply the conjunction rule, and this is a conclusion of the conjunction rule. Here you have conjunction rule, so you need a disjunct. Sorry, typo. You can see I am really reading my slides, and what I did, I made a mistake here. Rule is disjunction, and conclusion of should be disjunction. This is a little typo, but it happens. And how I noticed this typo? Because I thought, oh, disjunction, conjunction has 2 premises, and here I have only 1 premise. Something wrong. Typo is here. So axiom, here, for example, you have conjunction rule. So you say that you have two axioms and you apply conjunction rule. And you have, so you get a conclusion, then you have another rule, and now conjunction is two premises rule. So you have the conclusion, then this is one premise rule, and then you have whatever you get at the end. So we write those, we'll be writing those proofs as trees where there's more information than in normal proof that, remember, you had to fill the gaps with horrible difficulties. So, and in a sense, those proof trees represent a certain visualization of the proofs and the proof search. Because, for example, I will give you a concrete example. Here, this is the Morgan law, and here's the proof. We start the proof from the bottom, because this is axiom. You see, here's the axiom. I apply disjunction to, for example, this is gamma prime, so I can apply disjunction to those two pieces, because this is gamma prime, literal. So I write this, and here I have an axiom. I apply disjunction also to those pieces. You see, in this way, they are the same. So you see, you need to have the same information. This is the delta, and now I can apply conjunction to those two pieces. So I have conjunction, and now I can apply double negation. Gamma, here gamma prime is empty, and to the first one, I cannot do it to the second because the rules have those gamma prime. So if you apply A, here your A, if you want to, if you have the sequence A and B, here is and not A or not B, so now my A is here and gamma prime is empty. I cannot apply double negation to this because here is this is not gamma prime. So I can only apply to the first on the left. So that's why you can apply conjunction only here and double negation only to this formula. You have this, and then you have negation of this, comma, this is not A and this is B. You have you apply implication, so that would be our not A and B implies. So that is how that proof you read from the bottom to up. But when we are thinking about those trees as a proof searching trees. And now I am going to explain you that what we are really doing when you look at this proof, the system allows us, for example, I have, wait, I'm going to put this and to be more comfortable. So, search for proof. For example, I have my not A and B implies not A, the Morgan law. And can I prove that in our proof system? Each search here, main connective is implication. So I have only one rule possible, which would give us that conclusion. What that rule says, that you have not A, B, and not A or not B. So you can see that now we go from here. I said, oh, if I had a proof, it must have been only implication. which are the premises of implication? Not A, which would be double negation of this, comma B. And now, again, you say, oh, and here you have gamma prime is empty, and here you have gamma prime is also empty. And now, if this had a proof, the only possible rule would be double negation. So what does it mean? Not A. The rule is that you have A and B. The rule goes from bottom to up. Our search is from top to bottom. So if it had a proof, that can be only by that rule. So I just write the premises, and this is conclusion of double negation rule. And again, you keep going. Here again, you have gamma prime is empty, so you have to look at the first one. And if this had a proof, it would be only by that rule. What this rule says, that conjunction is two premises rule. So I write conjunction. One premise is A, and the second B. And this is my information, which you carry. So that would be not A or not B. And here would be not A or not B. And now you have two branches. That's why we build those trees. They're like visual, beautiful visual way of building the proof. Now, here you have gamma prime is this A. So you look at the formula, which is here. Oh, if this sequence had a proof, it would be only by the disjunction rule apply to not A, comma, not B, and information is carried, and you have variable negation, you have an axiom, and you have the same here. If it had the proof, it would be only by the only one rule, which would say our information is B, and here you have not A, not B, and again you have variable negation, you have axioms. So that's how I got that tree as an example of formal proof. So really those this type of proof systems are designed to search for proofs. And you can see it's a beautiful search for proof. And now we are going to be more, of course, when this is like the tree proof is a new notion because it has more information. It's a tree. You have the name of the rule and so on. So you have this beautiful information. You don't need to think. Your proof is also with the full information. Of course, the formal proof, because logic deals with the formal proof, you can write a formal proof. It means your formal proof is what? Axiom, axiom. So you write axiom, axiom, and then you write what is from the axioms, and then you write from what is in the axioms, and you keep, you can always write a formal proof. You see here, if I give you a formal proof like that, you would have to think much more to reconstruct the proof as what really is happening here. So that's why we are talking about tree proofs, because you have this beautiful easiness of information and the way you carry the proof. And search of the proofs, I give you more examples. And here is the search of the proof. You have nice tree of another, and then you have, for example, now those search proof trees are called decomposition trees, because you see they are called decomposition tree. So the search of proof is constructing decomposition tree. So this is a decomposition tree, And this is our decompose, because you have a formula and you use the rule to decompose into sequences, and you use, so these are called decomposition tree. So for example, you have a formula. So proof search in those system consists of building these decomposition trees, and you can write a program very easily, and I'll give you algorithm. So for example, here is a decomposition tree, and also what you can see here, decomposition tree you build, here is an axiom, and here is also, oh, this is not an axiom, you see? So this is not a proof. You decompose a formula, and you didn't, this is a decomposition tree, which is not a proof, because that is not an axiom. So that's how you can, and then because your decomposition tree is unique, if you get no non-axiom, it means that the proof does not exist. So here is just a little bit more language. So the process of searching of proof of the formula consists of building decomposition tree, and we defined what you do really. You change the inference rules into the decomposition rules. You can see here those decomposition rules are the inverse, where you exchange. That was premise, you have conclusion. So you have conclusion, you change into the premise. So this is here, you use the decomposition rules. So you can write those decomposition rules. And this is characteristic to all of this type of proof systems. That's why they are called automated theorem proof systems, because you can decompose the formulas and get proof or not, depending on how they are. So, and you see, because we want to have this pretty trees, because if you have like that, you can really see what's happening. You can write this decomposition rules as a pieces of the tree. So it's just exactly what's happening when you do your problems. So I wrote it a tree rules, how to build a tree. So if you write your program, you can do some graphics to have as an output these beautiful decomposition trees. So, and also the names are exactly. So the other things which is important, that there's some, okay, what is important that in this system we built those for any formula, the decomposition tree is unique because of this gamma prime. You can only have one. At each moment, you can have only one formula to decompose. So to formulate it in a nice formal way, we have new words. It means we have a sequence gamma prime built only of literals is called indecomposable sequence. There's no rule to decompose. So you have indecomposable sequence. A formula which is not a literal is called decomposable formula, right? Not literal. Literals are indecomposable. A formula which has a connective which can be decomposed is indecomposable. Remember, literals are one negation, is variable or negation. So if you have double negation of variable, it's decomposable because you can get rid of double negation. And the sequence which contains decomposable formula is decomposable sequence. So you need to introduce, if you want to prove theorems about it all, you need to introduce a proper language. And for observation, for any decomposable sequence, there's exactly one decomposable decomposition rule applied to it. The rule is determined by the first decomposable formula. Here's here is your first decomposable formula because gamma is empty. And here, your first decomposable formula here is, this is gamma prime, this is indecomposable. That is a first decomposable formula. And if the main connective of the first decomposable formula is without negation, like here, you just build the tree, as it says, putting the premises below. And if the first is double negation connective, so you look at the second connective and you apply the formula. And you have decomposition lemma immediately, that for any sequence, of formulas, if gamma is a sequence of literals, or gamma is in the domain of exactly one decomposition rule, this rule is determined by the first decomposable formula and by the main connective of that formula. So that is important to notice because the rules were structured like that. And now you have the proper definition of decomposition, of decomposition tree of a formula A, if formula A is the root of the tree, and if gamma, for any node, other node gamma on the tree, we have the steps. If it's indecomposable, it becomes the leaf. If gamma is decomposable, then we traverse gamma from left to right. Why? From left to right, because you have those gamma prime. So here is empty, so you always traverse from left to right to find the first connective or the first decomposable formula. Here you traverse, this is gamma prime, so you traverse from left always, and here was the first, here's the same, here's the first. And by the decomposition lemma, there's exactly one decomposition rule determined by the main connective, and we put premises on the node below, left and right premises, etc., as we did. So this is a nice general definition, and here is example isn't a definition, so sometimes you need a little bit more language to be able to word the proper definition. And immediately we have, you can see how easy, sometimes you have very easy theorems to prove. We already proved it, that decomposition tree theorem for any sequence is gamma, tree of gamma. It's not only formula, because if you have sequence, you go formula by formula. Tree is finite and unique. Question. Why? Finite, right? This is an example that is finite. Why? We already proved that it's unique because of this gamma prime. Why is finite? Think for a second. Why always gamma is finite? And because it's unique, gamma is a proof, if and only if, of Leaf's axioms. And if gamma does not have a proof, if and only if has a non-axiom leaf, right? So that means does not have a proof. So because tree is unique, so it doesn't. If you find a non-axiom leaf, not only that what you found is not a proof, it means because the search is unique, you will never have a proof. So that means the proof does not exist. And there's repeated what I just said. And you have examples, and you can see I'm not going to repeat it, but it's exactly what was on the blackboard. We started with that, and I put little square around the main connective to show that you find the main connective, you apply the decomposition rule, and you keep going nicely to the next, and then you have this. So you have the first formula on the left, and you keep going, building your tree. So you have a nice tree. And see, it's easy. It's visual. It's very piece. And also we have a nice theorem of uniqueness and so on. Now the next, what happened? What happens when you have this tree? You see, now we have this tree, and I'm going to erase this, which we built that decomposition tree, and that decomposition tree is unique and finish and has one non-axiom leaf. Oh my. Okay. Right? And has non-axiom leaf. You see, this is non-axiom leaf. It means by our theorem that proof does not exist. So it means that the proof does not exist. And here you have a completeness theorem. Completeness theorem says that we know has a proof if and only if is a tautology. This is completeness theorem for sequences. Now, we have a very important property of our system. Remember when I was writing you here, when we looked how to remember the rules, I was writing, for example, something like that. B was logically equivalent, A implies B. It means here you have a premise, not A, B, and here you have conclusion B, and because in classical logic you have that implication is logically equivalent to not A or B, so you have that this premise is logically equivalent to conclusion. So, and all of them have that property. So, and this is very important property. So we have definition for any proof, new notion, for any proof system. We say that the rule of inference of a given proof system, rule of inference, that is any proof system. We say that a rule of inference such that conjunction of all premises is logically equivalent to conclusion is called strongly sound, right? You have in our system, you have, for example, not A, not B, and the rule would be not A, B. One premise, P1 and P2 is logically equivalent because not A and not B by De Morgan law is not A, B, right? So here you have two premises. Conjunction of premises is logically equivalent to a conclusion, and here you have the Morgan law. So this is modus ponens. That is next thing to remember. So this is logical equivalence. Now, modus ponens is not strongly sound. If you have modus ponens, what is modus ponens? You have A implies B, and you conclude B. This is our Hilbert-style modus ponens, which you cannot use for automatic theorem proving. A and A implies B is not logically equivalent. B. Exercise. Very difficult exercise. So the notion of strongly sound, so if you have modus ponens is not strongly sound. But if you have that A is T, A implies B is T, then we get that T implies B T if and only if B equal T. So modus ponens is sound, but it's not strongly sound. So we have a new notion of strong soundness. And this is very important because that's why we can build the counterexample for the decomposition trees. And then, you see, all the rules of RS are strongly sound. Here is a beautiful proof in colors. That is very easy. Now, here is a little bit more complicated. I wrote that proof in detail because you can see to be able to do it, for example, you use the distribution of disjunction over conjunction. So here in red, and then you use the De Morgan law, and that's how you prove the strong soundness. So this is a little bit of work, but it's not a big work. So this is, again, you need distribution law, law, and you need the Morgan law to prove the soundness of the rule. And strong soundness, of course, implies the soundness, and we have a strong soundness theorem for our system. Is if has a proof, then is a tautology, and in particular for the formula. So so you have also a strong soundness, and here you have if and only if for strong soundness. And now we have what is called countermodel theorem, that if we have a decomposition tree, if a decomposition tree contains non-axiom leaf, that any truth assignment that falsify the non-axiom leaf is a countermodel by A. And here I will show you a nice example. Right? We had the tree. For example, this tree, we already did it. This is non-axiom leaf. And now what's happening? Take a variable assignment which put the leaf f. This is logically equivalent to that. So this f goes up. Now, by strong soundness, that sequence is logically equivalent to that. F goes up. Now, this is a conjunction. If you have F, and whatever is on the other side, you have F. And then you have strong soundness. So if to build a countermodel for a formula, it is enough to put the leaf into F. And that is what we called countermodel theorem, that if we want a countermodel, first of all, if A is such, it means the proof does not exist. TA contains non-axiom leaf, any truth assignment which falsify leaf, non-axiom leaf, is a countermodel for the formula. And now we have to put, so when we want to prove the completeness theorem, it means completeness part. Because you have soundness, so you need only to prove the completeness, you need to prove completeness part. So which says if A is tautology, then it has a proof, and instead we prove the opposite implication. It means A implies B is not B. So if A does not have a proof, that A is not tautology. So from the information that A does not have a proof in our system, we can show that it's not a tautology. It means we built a contramodel. And here's the contramodel. And this is called, now, again, I can make you another little drawing to remember. So that is only possible, I repeat, where the system is strongly sound, because this F can walk up the tree. So if you have a tree, a gamma, 3A or 3 gamma, and 3 goes whatever it goes, 1 premise, 2 premises rule, can be very big. And when you have somewhere non-axiom leaf, 1 is enough. So it has literals, right? So it has some literals and negation of literals, but you never have variable and negation of variable, right? So this is non-axiom leaf. So it's enough to put this non-axiom leaf into F, and this F travels the tree because of strong soundness. This is logically equivalent. Now that is a conjunction. So conjunction, whatever you have here, you can have T. Conjunction is F. So this F travels the tree. So you have F always travels the tree from the from non-axiom leaf. So and here is a general way of defining a contramodel. What does it mean? Now, there's another reminder that what is a contramodel? Contramodel is V, which has all variables into TF such that V A equal any V is called a counter model, right? So now when you have an axiom leaf like that, I want to put it into F. What does it mean? That you put V on a variable here. On A must be F, on B must be F, not C must be F, and not D must be F, right? So what does it mean? C must be T, and D must be T. So if variable is with negation, so T when X is with negation, and you put F when X is just a positive literal. And then you see here, this is called restricted. These are the variables, only 4 variables. V, the domain, is the set of all variables. So you can put here anything you want. So it means T, F, whatever, any combination, because that restricted variable assignment is a model or contramodel for the formula if the formula has. So it doesn't matter what you put on other variables. And you can always need to extend that assignment on the finite sequence of variables to the set of all variables. And that's why you define like that. VA equal F if A appears on the leaf, T if negation appears on the leaf, and any value if A does not appear on the leaf. and so on. So that's our proof. That's the shortest proof of completeness theorem, which sort of, I think, exists. Read chapter 5, proof 2. Even 1 we covered in detail, but read chapter 5, proof 2, and then you will fully appreciate the shortness of that our proof. Now, there are some variation on the system RS, and I just want to, we change the rules a little bit. It means, for example, now what you do, you keep the same axioms, but now what you do, you put prime not here, not gamma prime. Literals are not at the beginning, but at the end. This is a different proof system because the rules are totally different. So this is a different proof system in all the rules. So you say gamma, typo. It should be delta prime. You see, gamma now is in, gamma is any sequential formula, and delta prime is sequence of literals. So this is a different proof system, and construct a proof of the formula. Proof is strongly sound. Define in your own words for any formula the decomposition, and proof of the completeness theorem. Now, here is what is the difference that I want now to find the proof of this formula. First step is the same because you have only one main connective, is implication. But now our prime is on this side. So delta prime here is empty. So you have to go from the right and look at this. Gamma prime was on this side, so you went from left to right. Now, because you have gamma prime, you have to go from the right to left, and you look at this. And now these are literals, so it's delta prime. You can go here, and you can decompose, and you have. So this is a small difference, but this is a syntactical difference. So and then you can. I just wanted to show you that it sounds, proof strong soundness. What it is, you take the same, but you put prime on this, and the rest is exactly the same. So very often, things which seem extremely difficult are just slight. You have to rewrite slightly your proof, and you get a beautiful proof for other system. Now, and then you can write the decomposition tree. Now, when you write the decomposition tree, you traverse resulting sequence on the new node of the tree from right to left. And in the first system, you went from left to right. So this is just, and then the rest is exactly the same. Right? You have uniqueness because you have those primes, everything goes the same. Now, the other system, you just skip primes. So you do that, you change gamma prime into gamma. So you don't have primes at all. You don't have literals. It means that you can decompose any formula in the sequence. So you can have many possible decomposition trees. For example, you can see how I decompose, like you have here. Here I decompose on this side, but you could also decompose, which way? Let's see which one. I decompose this one. Because I already wanted to have here, I decompose, yeah, I was going from the left, but you can decompose also from this side, and I think you have another tree where I just decompose in the different way, because if you have two formulas, you can decompose this or you can decompose that. So I choose to decompose that. And then you have two formulas, you can decompose, this is a typo. You can decompose this or you can decompose that, so you have many decomposition trees. So there are many ways to apply rules of the decomposition, so you don't have uniqueness of decomposition. And then, again, you do exactly the same strong soundness. And now, if you want to prove the completeness, is a little bit more. What does it mean that here doesn't have a proof? It means every decomposition tree, any possible ways of searching proof, has at least one axiom leaf. Otherwise, there would exist a tree with all axiom leaves, so you have to cover all possible possibility of searching for proof. And then, what does it mean? Let T be the set of all decomposition trees, and we can choose only one. You need only one control model. So if you all decomposition trees, you choose arbitrary with at least one atom leaf, and you define exactly the same control model as we did before. And okay, and here, if you want a procedure, of course, that was a good student who nicely wrote a procedure, and you can play and you can write your programs for all those systems, whatever you want. But I put this is a procedure, and what the procedure, for example, says, I don't know, leftmost, you see? So that choose leftmost formula, it means you go from the left to right. So procedure provides unique tree because always chooses the most indecomposable formula for the choice. So you can prove completeness as you did for RS. Now we are going to talk about the Gentzen sequent system and prove everything we did before we can do for that sequent system, but it's a little bit more complex structure. We will do two system GL and G for classical propositional logic, which are inspired by our original Gentzen, which is closer or very close to RS system, as close as possible. So, but they are based on sequence. So let's now define what it is. And also, yes, components. Language is our normal language. We add to the language a Gentzen arrow. So language is our normal language, and we now consider an extra language to which we add a arrow, long arrow, which is called the Gentzen arrow. That's why also, which I was so vehement from the beginning of the course and in the book, to use that symbol for implication, not this symbol, which is often used for implication, which is correct, very good symbol. You can use many symbols, because I used that, and that's why in my language is this symbol for implication, because now I need that symbol for Gentzen arrow, which is a different symbol and different meaning than our normal implication. So that's why the syntax is very important to have a precise syntax. So so now we add to our language our new symbol, and we create something which are called sequence. Sequences are built out of finite sequences, empty included, of formulas and the Gentzen arrow. And of course, we write finite sequences. We write gamma, delta, sigma, as we did before, of L. And now sequent is such an expression already now to our new language, which is finite sequence, arrow, and finite sequence, antecedent and succedent of the sequent, or often is called left side of the sequent and the right side of the sequent, just to make it simpler. So semantically, and you can see our in our RS system, the sequence was interpreted as disjunction. Now, sequent, sequence of formula, arrow sequence of formula, semantically is this comma is conjunction of the left side and disjunction of the right side. And that arrow becomes an implication in the semantics. So you can see the semantics is more complex. And also, if you have empty on the right side, it means that it yields a contradiction, and empty on the left side, it means on the right side is T implies disjunction. And empty sequence, just empty, which is gamma and delta can be empty, represents a contradiction. And we have a nice notation. We already, if you have sequences, you write delta or sigma for conjunction and delta for disjunction. So the sequent would be semantically as conjunction of gamma. Conjunction of gamma implies a disjunction of delta, and we will use that symbols. And of course, now formally we can extend our truth assignment now to the set of all sequents, as Q is the set of gamma implies delta of sequence. How V star of a sequent would be equal V star of conjunction implies V star of disjunction. So now we have a semantics, and we can, and of course you have special cases when gamma is empty. So V star of empty is you treat empty as a T. So this is T implies disjunction. And if delta is empty, you treat that empty space as a falsehood. And the model you have is a model if and only if V evaluates in T, so it means V is a model of a sequent. Countermodel is if evaluates in F, and tautology, because is a tautology that evaluates CT for all truth assignments. And we write tautology, gamma implies delta. For example, let's say you have a sequent, and you have a truth assignment. Now, by definition, and I want to know if this truth assignment is a model for that sequent. So V star of the sequent, by definition, is V star of conjunction of this and disjunction of this. So on this side, you have VA conjunction of all formulas, and I already distributed. So this is conjunction. And on this side, you have disjunction. In short notation, you can go immediately to a short notation would be T, and T, because you have this conjunction, implies not T, or now the comma here is or, T implies T is T, so that V is a model. So it's a little bit more complex, but not too much complex. And you can see that that V, which we assign, is the only one for which the left side, this is true. So this V is the only truth assignment for which that part is true. It means and we show that it's true. And we know that implication is false only if truth implies false. So you can see that model, it's impossible to falsify because the other part would be also always true. So we prove that this is a tautology. And now, next thing important, I think part of things you can really learn, there's many things you can learn from from logic, but also you can learn that you always have to define your notation. Like, for example, here you also use gamma prime, but now finite gamma prime are finite sequences formed out of positive literals. So a sequence is indecomposable. So gamma prime in RS, gamma prime were literals. You could have variables and negation of variables. Now, in this system, gamma prime is only variables. Gamma prime delta prime is a sequences of variables which we called positive literals. So sequence is indecomposable if it's formed out of indecomposable sequences. So it means gamma prime implies delta prime. These are our indecomposable sequences. You have only variables. And then I reminded you that that is only positive literals. So logical axiom now is the sequence which has the same variable on both sides of. So that corresponds, when you think in intuitionistic logic, in L3 logic, in hating logic, A implies A was always a tautology. For different semantics, A implies A was always tautology. So here, that fact that that is an axiom is much more general fact than the axiom of RS, which would correspond to A or not A. So already here, that system, the whole framework is more general than the beautiful RS framework which we had for classical logic. So I want to, and again, this now primes are sequences of variables. And here, semantic link. I want to prove that axiom is tautology. Take any variable assignments. V of this, you can write a shorthand, would be conjunction of all gamma prime and A, and conjunction of all this. So this is the left side. Arrow, Gentzen arrow is implication, and here everything is disjunction. So you have disjunction of this, or A, or, and I want to show that this is T, always for any V. When you look at this structure, how this is structured, this is subformula A, you see, which repeats, and variable A, and formula B, and here is C, or A and B, and this is a propositional tautology. You can do by proof by contradiction. So really it is the fact that axiom is a tautology is based on that simple classical tautology. So they are tautologies. And now you have inference rules. And now the inference rules are two types. In RS was connective and negation of connective. Now you have introduced connective on the left side of the sequence, left side, AB becomes AB, and another rule is introduction on the right side. So you can see, so you now duality is introduce a connective on the left side and on the right side. The same for implication. you introduce, this is easy because you know that the semantics of comma is disjunction, and introduction on the left side of the arrow is more complex, and the same for implication. So that really represents that implication. This is implication. Like everything is empty. A Gentzen arrow B is A, B, it means true, implies A and B. So, and now you have two negations. Negation flips from left to right. If you have A on the left, it flips to the right with negation, because A implies B is logically equivalent, not A or B. So implication B implies A is not A implies B. So, and you have negation rules, and the proof system is all this. Right now, we built our proof trees as we did before, and the search is building the decomposition trees. Now, immediately, here is, you have those primes, but they are still, don't give totally uniqueness of decomposition tree. Just to bring that to your attention, I show that this is the one tree which would be the proof of the Morgan law, and then there's another proof which is different of the Morgan law. So the decomposition trees are almost unique, but it's not always unique. So searching for proof is building the decomposition tree. So of course, formula A generates a finite set of decomposition trees. And if there exists space, a tree, who all leaves the axiom, this tree is a proof. If all trees have at least one non-axiom leaf, the proof does not exist because you have many searches. So if you find a tree with all axiom leaves, you are okay. If not, you have many possibilities, so you have to run through all the possibilities. If none of them would give you an axiom, that proof does not exist. So uniqueness gave you less work to do. And then, of course, you do the same as we did before. It means that you use the decomposition rules instead of inference rules. And then I think, I didn't write. So, and you can write those decomposition rules as a tree decomposition rules. So you know how to build a tree. So that would be tree decomposition rules. So you use the decomposition rules, and you build the tree definition. Decomposition is built, the sequent is the root, and then if it's indecomposable, that becomes the leaf of the tree. And now what it is, you traverse from gamma, from left to right, to find first decomposable formula, and the main connective identify the rule on the left, and we check if this decomposition rule applies. If it doesn't, if it does, we put the conclusion as a leaf or leaves of that node. And then in gamma, in delta, when you look at the trees, you see here you have gamma. So on this side, you have prime here. So to find the rule on this side, you have to traverse from right to left to find decomposition. If you want to find a first formula on the left side, you traverse from left to right. So that is the difference, that you have to, if you want this type of rule, you have to traverse from right to left to find that implication. If you have to find this, you traverse, because this is gamma prime, you traverse from left to right. And that is for all the rules. You see here you traverse from left to right, and here you traverse from left to right. From right to left to find the rule. You see the first formula, which is decomposable, and here you traverse from left to right to find that first formula, and you decompose the way the rule says to decompose. So that is the difference. And also when you look at decomposable sequence is always in domain of one of the decomposition rules, or from the left or from the right, or it can be in the domain of both of them. And I think that I gave you, if you want to construct that, so this is a formula. So you write, the formula has a proof if you put the Gentzen arrow. So you construct the tree, and now you go from the left or right, and you get all the axioms. So here I look this is my main connective, so that implication becomes Gentzen arrow, and now I go from left. I can go here from this side, I can decompose this. Oh yeah, I can decompose that, because here you have delta prime is empty and gamma prime is empty. So here you have two choices. You can decompose this, or you can decompose that. But I choose here to decompose that formula. So I use this rule, and that rule says exactly where to put node B in front. And I have that. And now this is in decomposable. So now I traverse here. That is decomposable, because in decomposable is only variables. So here my first is negation. And negation switches exactly not after A, but before A. So you have to look at the rules. And now I have only one rule, is this. And the main connective is implication. I decompose, and now this is not the end, because I have negation on this side, which pulls this on the other side, and here you have axiom. Axiom is the end of the tree. So it's a little bit more. If you write a good program, you don't need to worry where. But if you write a program, you have to be very careful, because the rules tell you exactly where, if you switch, for example, negation, where, like, for example, if you decompose that negation, you see it says that A, you get rid of negation, put after decomposable. So you put not on this side of gamma prime, you put here. And the same on this. If you have this, you don't put anywhere. That A goes between already in decomposable and decomposable. So you see, all rules tells you exactly where you switch and where you put your formulas when you decompose. So it's a nicely, a little bit more. For example, here I give you all proofs of the tree. Oh, that was a nice example. Yeah, so that's write all proofs. And also find the formula which is unique decomposition trees. When you look at the structure of the rules, certain connectives would give you, a combination of connectives would give you a unique tree. The other combination would not give you, so this is just to make you think of the structure of the rules. Now we have soundness and completeness we want to have, and we want to have constructive proof, as we did. Now, these horrible rules are also strongly sound. So, and of course, I wrote what is strongly sound, that you have conjunction of premises is equal, the value of conjunction of premises is equal the value of conclusion, and so this is our strong soundness. Now, to prove the strong soundness of the rules, for example, I will need all these basic classical equivalences. And here I listed them. We proved them in chapter 3. All this, maybe not all, but at least I listed them a lot. But these are the basic tautologies. It means equivalences, logical equivalences. Logical equivalence, that it means that the value is the same on both sides. So, for example, you want to prove the strong soundness of this. That is easy, because conjunction is conjunction. But to prove the strong soundness of this, we have V of this. This is a conjunction. And you have, this is this premise, this is that premise. Now, when you distribute V, you get all this. And now you can see the structure. I can say that the structure of this is A implies B. A is this, B is the whole thing, this end is this is A, and this is my C. So I have that part is A implies B and A implies C. And now I use distributivity here, and on this side, that would be A, you see, and that is B implies C, not this B, but B here is whatever. C was this, and B was the whole thing. So you use this and you prove that this is A, and this was this B, and this B is the whole thing. Oh, here I have the distributivity, yeah. So this is B and C. And so I can prove, that proves that this is strongly sound. You use the commutativity here and distributivity. And here's even more complex. So spy with your little eye all the steps, why they are correct. And again, this is another one, and this is the propositional equivalence, which we use to prove that, and we can go and prove all the rules like that. So you have soundness theorem, and you have strong soundness, not only. So I know that we need the strong soundness in this system in the same way we need it with RS to what? To have F climbing the tree. Remember, the strong soundness was needed that we have a decomposition tree, and we have non-axiom. And if we put non-axiom leaf on F, our F would climb the tree. So, and this is counter model for our sequence or formula A. It's enough to, so we need the strong soundness. F climbs the tree because of the strong soundness. That's why we had to, once we have a strong soundness, we can do exactly the same what we did before. That's why we struggled to prove the strong soundness. And that's what I say, that if you do the leaf, you can falsify the contramodel of the tree, and this is called contramodel determined by decomposition tree. So that is, so given a sequent, such a decomposition tree contains non-axiom leaf, and a truth assignment that falsify non-axiom leaf is a contramodel for the top. So that is exactly the same. Because of the strong soundness of the system, we have the same theorem. And in particular, given a formula, the decomposition tree of A has with non-axiom leaf. Let us define the contramodel of A, or it can be contramodel for the whole sequent. And so exercise, we know that G is strongly sound, proved by constructing contramodel determined by the tree. So here is your tree, and here's non-axiom leaf. Now, what does it mean that we have to put that sequent into F? We put the sequent into F, it means that I want to have V, which V star of the sequent is F. But by definition of semantics, if that part is empty, it is represented by T. So you have T implies value of B, value of B, value of A. So that is F, if and only if that part is F. So it means that the disjunction has to be F. It means that B has to be A, F, and value of A has to be F, and value of B. So that would be a contramodel. And you can see immediately that what does it mean? This is the disjunction. Sequent, now, shorthand. That is shorthand for that. You want to do it fast. You say, I want, you have A, or you have B, B, A, and I want to put it into F. So by definition, empty here, it means T implies B or A, must be F. So this is how we define the semantics. So that is if and only if the whole thing is F. So B is F, A is F. So this is a shorthand notation of a proper description. Oh, you see, and here you can see I put F, and the F by strong soundness. Now the F became red, is climbing the tree. And completeness theorem for the formula is this, for the sequent is that, and you know a formula has a proof if the sequent built out of only formula has a proof. So if you want to prove that we prove the opposite implication, that A does not have a proof, then it's not a tautology. So what does it mean? Does not have a proof. What does it mean that the formula or sequent does not have a proof? It means that let T be the set of all decomposition trees, does not have a proof if each tree in the set has a non-axiom leaf. We choose an arbitrary tree, and let's LA, the leaf, non-axiom leaf, would be gamma prime. Remember, they are only variables because that's how we defined the stop on our search, be non-axiom leaf. And what you do, you have to, what does it mean that so this is if that is true and that is F, right? This is a conjunction. This is a conjunction of all variables. So it means all variables in gamma prime must be T, because this is a conjunction. And here is disjunction, so it means all variables in delta prime are false. And that's what is in general. You put falsify this if it's T, if A appears on the left side, all variables here to be true, and F if A appears on the right side. And then by control-model theorem, we prove the completeness. So it's a little bit more work, but it is not. And now we can have a little bit closer to a little bit more relaxed system, let's put it like that. So again, that means that if I build decomposition, if I take axiom like that, it means that indecomposable are only variables. So I know where. And now I use exactly the same rule of inference, but I don't care about gamma prime, delta prime. So I have something here, and I have something on this side, and I can do whatever I want. I can decompose any formula on the right side, on the left side. And usually in the books, that's what you get as a Gentzen system. You just do whatever you want in any, so you have just a little bit more decomposition tree. So, and then you the same, explain why it's strongly sound. The fact that we had these primes there didn't change any proof of that. Proved, as an example, soundness of 4 rules. You can use the same rules I show you. And so the strong soundness of G, defining the decomposition tree. Now decomposition tree is a little bit like in our RS2, you can decompose on the left, on the right, any formula you choose. So you construct much more decomposition trees to show that the proof does not exist. And then you just extend the whole definition to the system. And also give an example of formula such that tree is unique. And another that tree is not unique. And you have the same, you can prove our decomposition theorem. So everything we did, we can do for that. Just the set of all trees, again, in this even more, that if formula or sequence does not have a proof, it means that you have to consider all possibilities of search. So each decomposition tree has a non-axiom leaf, and then you pick up one to construct a control model, so it's exactly the same. Now, I want to finish by just showing how the rules of the original Gentzen, which are a little even more complex. It means that you have sequence. The beginning is exactly the same. Now, logical axiom is A implies A. So these are sequences of formula, but logical axiom is just A implies A. One formula implies formula. And now we have a structural rules, which is weakening, that here is you can add formula on the, always you can add formula on the left side. As a decomposition rule, you can cross out A. That's why it's called weakening. Because when you think about this rule as decomposition, you lose A. If you go from here to here, A disappears. And the same here, A disappears. And then you have contraction. If you have double A, you can do A, and the same here. So you can, and they are very important in Hauptsatz. So you have exchange. So it doesn't mean you can always exchange the formulas. And you have do the same on the other side. And you have a cut rule. So Gentzen, to prove the equivalency of his system with Hilbert complete system of classical logic and intuitionistic logic, other system, he needed to introduce the modus ponens. Cut rule is really a modus ponens, because you can see this is something implies A, and A is on this side. You can cut the A. So that is modus ponens is a case of that formula, because you have not A. here you have A implies B, and you cut A, and you have whatever you have here, and you have whatever the B would be, whatever you have. So this is called cut formula. So he introduced that cut formula, and then you have conjunction rule. For example, now, because you have only one formula, you have two conjunction rules, and also you have two disjunction rules, right? Because you have A, you can always write A or B, and you have B, A or B. On this side, you have only one rule. So you have a negation rule is the same, and implication rule is the same. And he said exactly that his system is structural rules, cut rule, and logical rules. So all these rules. And what is the power and his genius was that he proved that if you take only sequence such that on the right side delta consists at most one formula with all the same rules, with those restrictions, you get intuitionistic logic. And also he did it for quantifiers, so we'll study the full-fledged predicate case later in chapter 9. So we just say LK is a logischer calculus, and this is intuitionistic calculus. You get, and now you have the same tree. You have the trees, and now you can see when you want to do, for example, you want to decompose this. You have this junction, so. For example, you can have contraction, so you have a double the formula. And now I use disjunction rule for that one, so I have A. Now I can have exchange, put A here. Now I can use the disjunction rule here, and I have this, and now I put negation, I have an axiom. So you can see there's a lot of, that's, it's not, yeah, you have a lot of thinking how to do it. And there's another derivation. So just to, soundness is, of course, you have soundness, but you don't have a strong soundness because you don't have that A is not logically equivalent of conjunction, etc. So logical rules are not strongly sound, and contract and exchange are strongly sound because they are strongly sound. Weakening is sound, but it's not strongly sound. So these are different. And cut rule is sound. It's like modus ponens. Here, and of course, it's not strongly sound like modus ponens was not. And here's proof of soundness of cut rule. And you have soundness theorem, of course. And completeness, he chose, as I said, he chose to prove the completeness, showing that he chose the Hilbert-Ackermann system. I gave you this, and we choose another formalization. So he chose a complete proof system for classical logic, and then he showed that each proof from there can be carried in his system. So, and of course, and his rules can be proved in that complete system. So he said, my system is complete because any proof in one system can be transferred into another and vice versa. So that's how he proved. And here is the proof says Hilbert's proof system has 11 axioms and 12 axioms A, not A. and then we prove that for any formula, of course, this is complete, and modus ponens in Hilbert style is really corresponds to cut, that form of the cut, right? If I have A implies B, I have B. So we have that if we have, we can get completeness theorem, we get the completeness theorem. That's how he proved the completeness theorem of his formalization. And then he showed the Hauptsatz theorem is cut elimination theorem. So he then showed that every derivation can be transformed into another derivation in his system of the same sequent with no cut rule occurs. And that proof is constructive proof by how you change through his structural rules, how those structural rules can replace, in a very clever way, can replace modus ponens. And so that is, and also you have for intuitionistic logic, you have the same, that every derivation of intuitionistic derivation can be transformed into another without the cut rules, and that is the Hauptsatz theorem, which is called main theorem. It's long, very involved, and the main important steps, I brought it in. First of all, you replace cut by what she calls mix. It means that you can remove many, you see here, you obtain from sigma delta by remove all occurrences which are commons. So he sort of said, if you have cuts, you can all do them at the same time, and he calls it mix. And here's an example. And then he shows that any derivation with mix can be transformed without mix. And this is, no, yeah. So I'm just showing, this is the only, the bare bone of the proof. And he does it rule by rule exchanges and so on. This is a long proof, but it's a very beautiful proof. And also, you see, I just bring this proof because, again, this is a purely structural proof. If you have a Gentzen type system for modal logic, for any logic you want to have this type of, you have the method how to go along with your rules to eliminate cut and to have Gentzen cut-free formalization. It means how you can have a system which is which admits the automatic theorem proving, and it's just pretty technical, but I think that you are ready to understand at least the whole idea of that on big screen. More details are, of course, in the book. All right, so that's the end of chapter 6. Thank you very much.